Hello, hello, good morning, hello, good morning, everyone. Let's today we will start solve and some exam paper. Now the first question read as, what is the difference between hypothesis driven and data driven? So we had differentiate it with the help of columns wise. Their first column read aspect, second is hypothesis driven, and the third one is data driven. Now the definition read is, in hypothesis driven, we start with a specific hypothesis, design data, collection, experiment to test it. But in data driven, we start with data, explore patterns, and formulate hypotheses from observations. Now the approach is, in hypothesis, it is deductive approach, confirm or refute a stated claim, while in data driven, it is inductive, discover patterns, then generalize it. The workflow is, in hypothesis driven hypothesis, then we do experiment, then collect it, then a statistical test is done. But in data driven, ingest data, then we go for EDA, then we feature extraction, modeling, hypothesis, generalization, validation. Data needs, in hypothesis, smaller control experimental data sets, in data driven often large varied data sets, logs, sensors, transactions. In model tools, in hypothesis, we use classical statistical tests, simple parametric models, while in data-driven, exploratory statistics, machine learning, clustering, ensemble, deep learning. Strengths. In hypothesis, it is clear casual testing with well-designed experiments, but in data-driven, it is good at uncovering unexpected patterns, flexible and data-centric. Weakness may miss unknown patterns biasly by initial hypothesis, but in data-driven, it is risk of spurious correlation requires careful validation and hold-out testing. Example, A/B test to see if new UI increases conversion rate. And in data driven, it is cluster user behavior logs to discover a high value user segments. Now we move to the second B part of the first question, that is, what is the difference between structured, unstructured, quantitative, and categorical data? So we divide it in four columns, and the fifth column is of expect. Now it starts with a definition. So a structured data, talking about the structured data, so data organized with fixed schema, row in column, can be stored in tables. Talking about unstructured, here data without fixed schema, free text, images, audio, any combination of data will be there. Talking about quantitative data deals with numerical values, numerical measurement. It will be continuous or discrete. And talking about categorical, which the data which can be classified, discrete labels or categories. Example, age, example, race, sex, color. Now storage format. In structured, it is relational tables, comma separated values, SQL structured query library databases. And in unstructured, text files are there, document stores, image, audio files, JSON, blobs, JavaScript object notations. And talking about quantitative, so as I already mentioned, it contains only numerical values, numerical columns in tables, arrays, time series, categorical, string labels, enums, quoted integers in tables. Now talking about some example of the structured data is that it is a customer table. We had one customer table in which there are several columns, for example, ID, name, age, balance. Now talking about the unstructured data, so it the example of it will be customer emails, product reviews, photos, call recordings, all in one. Quantitative, it is age, salary, temperature, number of clicks, all are in numerical format. And in categorical, it is country, product category, customer segment like bronze, silver, gold. Analysis technique. What are the technique for analysis? In structured, it is SQL queries, aggregation, joins, classical ML. In unstructured, it is natural language processing, computer vision, audio analysis, feature extraction. In quantitative, regression, correlation, hypothesis testing, distance-based models, chi-square test, frequency tables, encoding, classification, pre-processing. What are the pre-processing for required for that? So in structured is schema validation, typecasting, missing value handling. In unstructured, we first do tokenization, then stopword removal, embedding, image visualization, and normalization. And in quantitative, it is scaling, standardization, min, max, outlier treatment. And in categorical, one hot encoding or target encoding handles rare categories. Now moving to third question, third A, we had to compute mean, median, mode, standard deviation for a given small data sets, explain when each measure is appropriate. So we had to give its formula, mean, median, mode, and when we need to, when we use each method. Now start with the mean. So we have, for example, given a data set 2, 4, 4, 4, 5, 5, 7, 9. First, we sort the data in ascending order. Now, mean, we know that mean is sum of all the values divided by number of values. So if sum all the values, which gives 40, and number of values is 8 here. So we divide 40 by 80, which gives 5.0. So 5.0 is our mean here. I'm talking about median. So if the number of entries is even, so there here what we can do, we average the fourth and fifth values, that is 4 plus 5 divided by 2, that is 4.5. And if the value is even, we select the middle value. Now talking about the mode, so we know that mode is the most repeating value in the data set, a value with highest frequency. For example, here 4 occurs 3 times, so it is our mode. Now talking about standard deviation, for example, we have deviation from mean. We had calculated mean minus 3 minus 1 minus 1 minus 0.0024. Square deviation, now we square all the mean, 9 1 1 1 0 4 16. Now we calculate the population variance, that will be 32 by 8, and we then calculate its square root, which gives 2.0. Now sample variance will be 32 divided by 8 minus 1, that is 7. So it approximately will be around 4.571, and then we approximate it to under root 2.138 when each measure is appropriate. Now talking about when should each measure will be appropriate. Talking first, we start with the mean. So mean will give symmetric distribution without heavy outliers. So if the number of outliers is very less, then we go for mean. Now talking about median, so median is come for skewed distribution. If we have a skewed distribution or when outliers are present, then median is perfect for it. Then talking about the mode, so it gives categorical data on multimodal distribution. Standard deviation is the measure of speed. Use sample deviation when inferring from a sample. Now moving to question number third B part, it says this: what is the difference between errors and artifacts in data cleaning? So we know that when we clean data, there are two terms, errors and artifacts, and we have to explain any two imputation technique for them. So we first start with the definition. In errors, it said that what do you mean by errors? So incorrect or corrupted values caused by measurement problems, manual data entry mistakes, or transmission errors. Example, negative age, because we know that age cannot be negative, so it's just an error. And impossible date, for example, someone is talking about 2050, so it will very big value in case of dates. Now talking about the artifacts, so artifacts comes in case of data processing, when we process the data in cleaning process. So it is a systematic distortions introduced by instruments, the instrument which we use, data collection process, the way we collect the data of pre-processing pipeline. Example, batch effects in genomics, sensor drifts, compression artifacts. Now, what are its effects? Errors are often random or occur at a row level and can usually be detected through validation rules and range checks. Artifacts affects group of records in a systematic way and can bias analyze if not corrected. Now, what are the imputation technique? So we have two imputation technique: mean, median imputation. First, identify missing value in a single numeric column. Compute the mean or median. If distribution is skewed, then we go for median of non-missing values. Now third is replace each missing entry with this mean or median. Pros, it is simple, its advantage, it's simple fast, but its disadvantage, that is cons, is underestimate variance, can distort correlation. Now the second imputation technique is k-nearest neighbor imputation multivariate. Select a distance metric and normalize feature used for similarity. For a row with missing value, find k nearest row with that feature present. Impute numerical values by average of neighbors. For categorical, impute by majority category. Now its advantage is uses relationship between variables, and its disadvantage is computationally heavier, sensitive to scaling and choice of k. Now moving to question number 4. It reads that explain any four common feature engineering techniques for continuous or categorical data. So we had to discuss four common feature engineering technique. Now the first one is scaling, that is standardization is also called. Compute mean, median, and standard deviation sigma for each numerical feature. Transform each value x to x minus sigma or scale to 0 1 with min max. Helps to algorithm with data sensitive to feature scale KNN, SVM gradient. KNN is K nearest neighbor SVM support vector machine gradient descent. Now the second technique is one hot encoding for categorical various. For a feature with k categories, create k or k minus 1 binary columns. Each column is 1 if the record belongs to that category, else it will be 0. Required for many ML algorithms that expects numerical inputs. Now the third method is polynomial and interaction features. Create a new feature such as x square, x cube, or x1 times x square for selected variables. Capture non-linear relationship while still using linear models. Should be combined with regularization to avoid overfitting. Now the fourth method is binning discretization. Divide a continuous feature into intervals. This intervals means beans here using equal width or quantile cuts. Replace actual values with bin labels, example low, medium, high. Useful to reduce noise, handle non-linear effect, or build interpretable rules. Now moving to question number fifth, fourth B, which reads as what is sampling from a distribution? Describe inverse transform sampling or Monte Carlo sampling with example. So sampling from a distribution, the process of generating random observation whose probability distribution matches a specific target distribution, example normal exponential. It is fundamental to simulation and Monte Carlo methods. Inverse transform sampling. Now, what do you mean by inverse transformation? So there are certain steps. The first step is let f of x be the cumulative distribution function CDF of the target distribution. The second is generate u from uniform 0, 1. Set x equal to f minus 1 f की power minus 1 u, the inverse CDF quantile equivalent at u. Now the fourth step is random variable x follows the target distribution. For example, exponential lambda. So cumulative distribution function will be 1 minus e की power lambda x get 0 and in inverse f की power minus 1 u minus 1 lambda. For lambda 2 and u equal to 0.3 x minus 1 by 2 log n 0.s, so it will be approximately 0.178. Now Monte Carlo sampling. In Monte Carlo sampling, what we had to do, we had to draw many independent samples x1 dots x n for a distribution and estimate e of g of x that is equal to 1 by n sum of g of x of I used to approximately integrate the risks and probabilities that are hard to compute analytically. Now moving to question number 5 a, which which reads as what is the difference between parametric versus non-parametric models and what is the difference between supervised versus unsupervised learning. So we had divided two questions for parametric and non-parametric. We have aspects on what aspects we differentiated. Definition: in parametric, assume a specific functional form with a fixed finite sets of parameter. In non-parametric, does not assume a fixed functional form. Complexity can increase with data size. Now the example of parametric is linear regression, logistic regression, possessive naive bias, and in non-parametric we have k-nearest neighbor decision trees kernel density estimation. Flexibility. So parametric is less flexible, can be biased if the assumed form is wrong. But in case of non-parametric, it is more flexible, can approximate complex relationships. So data requirements for parametric is performs well with relatively small data sets when assumption hold. But in non-parametric, it is generally needs a more data, big size of data to avoid overfitting. Interpretability in parametric, often highly interpretable coefficients have clear meaning, but in non-parametric can be harder to interpret. Complex trees or instance-based model there are. Computation sometimes has closed form solution, usually cheaper to train, and in non-parametric distance computation or many parameters can be computationally costly. Aspect now we differentiate between the supervised and unsupervised learning. So the definition of supervised will be learn some mapping from inputs X to labeled outputs Y. In unsupervised learning, finds structure in unlabeled data X without explicit targets. Example of unsupervised learning will be classification, regression, example support vector machine, random forest we have. And in unsupervised clustering we done, K-means clustering, hierarchical clustering, PCA, association rule mining. Goal. What is the goal in supervised learning? Our goal will be predict or estimate the target variable as accurately as possible. But in unsupervised, discover clusters, latent factors or pattern within the data. Data requirement will be requires label datasets x, y, requires only features x, no labels in non-parametrics. Evolution of parametric. So uses metrics like accuracy, precision, recall, RMSE. But in non-parametric, it uses metrics like silhouette score, reconstruction error, or domain judgment. Use cases of parametric is spam detection, price prediction, medical diagnosis, but in non-pandemic it will be customer segmentation, anomaly detection, exploratory analysis. Now moving to next question, which reads as define accuracy, precision, recall, F1 score, and illustrate their computation using a confusion matrix. So first we have to create one confusion matrix and then we have to define what is accuracy, precision, recall, F1 score. Now the formula for accuracy reads as true positive plus true negative divided by sum of all, that is true positive plus false negative plus true negative. Now the formula for precision will be true positive divided by true positive plus false positive, and recall also called as sensitivity will be true positive divided by true positive plus f plus false negative, and f1 is called is two times of precision divided by precision plus recall. Now we had given one confusion matrix in which here the column 1 is predicted positive and the column 2 is predicted negative, and row 1 is actual positive and row 2 is actual negative. So the data is given. Now we calculate the accuracy. So we just need to put the values in accuracy, that is 50 plus 35 divided by 100, which is 0.85. Precision is 50 divided by 50 plus 100, 0.833. And recall is 50 divided by 50 plus 5, which is 0.9. And as I know, as I told you in earlier, that F1 score is 2 times of precision divided by precision plus recall, so it will give around approximately 0.8696. Interpretation, not talking about interpretation. Precision of all predicted positives, how many are truly positive. Recall of all actual positives, how many are correctly identified. And F1 score harmonic mean balancing precision recall. Now moving to next question, that is question number 8a. Compare descent trees, random forest, boosting column wise. So we had to compare all these three terms column wise. So first column we had taken the specs, now talking about their definition, their core idea. In descent tree, it is a single tree that recursively partitions feature space using slits. In random forest, ensembling of many trees, there are many trees on which we work. So built on bootstrap samples and with feature subsampling. Boosting, example of boosting is gradient boosting, XZ boost. It is a very famous say in each we the core idea is sequential ensemble where each new tree is trained to correct errors of previous trees. Now bias variance. So in descent tree there is low bias but high variance. It is prone to overfitting. In random forest, reduced variance relative to a single tree, similar or slightly slower bias. In boosting, it is typically low bias, variance controlled by regularization and learning rate. And training, fast to train, simple hyperparameters, depth, mean samples, parallel. In random forest, it is parallel training over trees, more computational intensive. In boosting, it is sequential training, often slower but very accurate. Interpretability, highly interpretable, easy to visualize. In random forest, it is less interpretable, rely on features, importance measure. In boosting, it is low interpretably, need tools such as SHAP for explanation. When to use? Descent tree we use when you need transparent rule-based models. Random forest, general purpose baseline for tabular data, robust out of the box. Boosting when predictive performance is required and compute is available. Weakness, unstable to smaller change. Decision tree overfits without pruning. Random forest, more memory and compute still may overfit if too deep. Boosting, sensitive to hyperparameters, risk of overfitting and longer training times. Now moving to next question, which read as explain the architecture and components of Spark, describe advantage over MapReduce. So what do you mean by Spark architecture? It is a high level architecture in which driver program, there are certain terms first we need to understand, that is driver program runs the main application and create the Spark session, Spark context. Then cluster manager allocates resource across the cluster, standalone, yan, yet another resource aggregation, resource coordinates, executors. Third one is executors that reads this worker process on cluster nodes that run tasks and cache data in memory. Now the fourth one is programming abstraction, that is RDD, data frame dataset for expressing transformation actions. The fifth one is scheduler builds are DAG'd, that is directed acyclic graph of strategies and target schedule them on executors. Now we differentiate between the Hadoop, MapReduce, and as Apache Spark. Processing model, in it we have batch processing with map and reduce stages. In Apache Spark, in memory DAG execution with lazy transformation and actions, support batch streaming interactive workloads. Now they're talking about the performance. So here high disk and network IO, slow for iterative or interactive algorithms. In Apache Spark, it keeps data in memory where possible, much faster for iterative ML and interactive analytics. Now API ease of use, low level map and reduce function, more boilerplate code. In Apache framework, in Apache Spark, it is high level API like data frame, dataset, SQL, ML, allow concise expression. Machine learning and streaming needs external tools. MapReduce alone is not ideal for iterative ML or streaming, but in Apache Spark, it includes ML library for scalable ML and structured streaming for near real-time processing. Thank you, friends. That's today. That's all. We had solved all the questions, and it will be great. Hope you understand it very well.